devices. I think it's a problem with the network that I was on, and hopefully we won't have any more of those issues. All right. Hopefully you guys can hear me now, and hopefully we don't have any more technical issues. All right. So a little bit of technical issues there. How's everybody doing today? How is everybody doing? So get to the chat, tell me what's going on, all that kind of stuff. I'm doing great, except for obviously we have to do all this online rather than in class together. It'd be great if I could see you guys, if we were all here together. But much, much more important than that is that we are all healthy and well. And I'm thankful that I'm healthy and well. And it's we should all do our parts to be safe and all that. Anyway, so hopefully can you guys hear me now? I am actually at school today. There's like literally nobody here. Because I just wanted to grab a few things, and I thought I might as well just do my streaming from school today. And so I just thought I'd go ahead and do that. Now, I'm having a little problems with the Wi-Fi here, so I'll probably do all the rest of mine from home anyway. But let's just go ahead and start off. Now, let me see. You guys hearing me? Boren says he loves me. Oh, that's awesome. I feel so touched. Awesome, awesome. All right, anyway. So let's go ahead and get started. Just want to say, first of all, that this is going to be just an addition to some of the stuff that you guys can already see online. All right. And so the video that you guys should have already seen or should see is Molarity Made Easy, obviously by Ket's book. So make sure you see that video at some point in time. This is going to be an addition to that, so you guys can see some of this stuff. But let's go ahead and the reason we're doing this is because we want to apply molarity to stoichiometry and do stoichiometry with molarity. If we were in class, we'd be going through this a little bit faster, but I really just want to slow down, stop, and just do a little bit of a review of molarity here today and try to apply that to a little bit of stoichiometry. And just slow down a little bit because we're doing everything online, and I know there are technical issues. I've had a little bit of technical issues myself here. What is the word similar than molarity? What does that question mean? What is the word similar than molarity? Yeah, I don't know. Molarity, so we're going to talk about this. Molarity, as you guys should already know, right, is M equals N over V. So that's the definition of molarity, right? And so N, as you guys know, that's going to be standing for moles. And then V, that's going to be your total volume of solution. And it's critical to remember that that's always going to be in liters. Okay, so the total volume of solution in liters. Oftentimes in the lab, we are going to measure volumes in milliliters, but that's going to be moles per liter. Okay, so let's just go ahead and, hey, look at this. Boren's online here. Look at that, Boren. You guys, Boren, you've already taken AP Chemistry. You have no need to watch this, but whatever, just for fun, right? Just for fun. All right, so I think you're thinking of molarity. Yes, I'm thinking of molarity. All right. Boren, I'm getting all these kind of positive messages from you. I feel just great. I feel just awesome. All right. So let's go ahead and just jump into today's lesson. Like I said, we want to do molarity, and we want to apply this to stoichiometry. Right? So we apply that to chemical reactions and all that. Okay. So let's jump into, and hopefully you guys saw these problems already on your Google Classroom. Okay. And so we're going to go ahead and solve basically the whole front page together. And then your homework literally is going to be the back page. So let's go ahead and solve the first one and the second one together here, and just talk about how these problems work. And hopefully you guys remember everything we learned about stoichiometry and molarity, but if you didn't, that's okay. We're going to do a little bit of review here. Okay, so let's just jump into the first problem. And we have 0.225 moles of sugar. So right away, we're going to notice, all right, that 0.225 moles of sugar, that's going to be our value of N. It's dissolved in water, so this is an aqueous solution, to make 500 milliliter aqueous solution, okay? And so this 500 milliliters, keep in mind, our volume measurement should always be in liters. So we're going to take this and divide by 1,000. It's so easy. We just take that decimal point, move it 1, 2, 3 spots to the left. And so remembering that there are 1,000 milliliters in 1 liter, so we're going to right away just write that's going to be 0.500 liters. That's going to be your volume of the solution. Okay? So the question is, what is the molarity of that solution? So if we're solving for molarity, we remember the equation M equals N over V, or molarity is moles per volume, or molarity is moles per liter, okay? And we just plug in the numbers. So that's going to be 0.225 moles divided by 0.500 liters. And this is one that you can literally do in your head, because dividing by 0.5 is the same as multiplying by 2, right? Or if you want, let's just go ahead and plug it in your calculators, right? So it's going to be let's see, here we go, 0.225 divided by 0.5, and that gets us our final answer for the first problem of 0.45, all right? 0.45. And because we have 3 sig figs, you should put another 0 after it. Now guys, what are the units? What are the units for this? You got to make sure you include your units. Anybody on the comment section? Will I take a sip of coffee? Anybody at all know the units? Yes, nice. All right, we got some correct answers. Moles per liter, and I'm sure there's actually a little bit of time lag. It's not you guys taking forever to answer it. There's just a little bit of time lag. So that's probably what's going on here. All right, so we have 0.45 moles per liter. That's your final answer, and we are good to go on number 1. All right, any questions so far? No questions. Let's jump right into the second problem. And we're going to look at this problem. We're going to do this more than one way, and you're going to see why we're going to do this more than one way here in a little bit, because we're going to apply this to stoichiometry. But number 2, how many moles of calcium chloride? Now, you don't actually need to even know what calcium chloride is to solve this problem, but just for fun, you guys know calcium chloride, of course, is CaCl2, because the calcium is a positive 2 and the chloride is a minus 1. But anyway, how many moles? So we are solving this problem for N of calcium chloride, or in 20 milliliters. Now 20 milliliters, that's going to be your volume, right? But your volume should once again be in liters. So that's going to be a volume of 0.0200 liters. All right? Of 2.18 M. That M stands for, and you're going to see this sometimes, the M stands for moles per liter. It's both the variable for molarity and the units for molarity. So you can always use capital M, or you can just write moles per liter. I prefer to use moles per liter, but you will see this sometimes when you read various different things. Okay, so it's 2.18 moles per liter, and so our molarity is going to be 2.18 moles per liter of calcium chloride. Okay, how many moles of calcium chloride is that? And like I said, there's 2 different ways that we can do this. And the first way is I'm just going to take that equation and rearrange it. So we have the equation that we've been using, M equals N over V, and we want to solve for N. So if we want to solve for N, we multiply both sides of the equation by V. So that is simply N equals MV, right? So that means we have a simple multiplication to do in order to solve for N. So it's going to be the molarity, which we already know, which is 2.18 moles per liter, times a volume of 0.02 liters. We have 3 significant figures there, but we don't need to write that down as we solve this problem. Okay? And so what you can do is you can just type that into your calculator. Again, this is probably one that you might even be able to do in your head too, but there's no need to do that because we can always use calculators. 2.18 times 0.02. Hit enter, and that's going to be our answer. 0.0436. We do have three significant figures because we have three significant figures here and here, so we're just going to keep it as three significant figures. 0.0436, and our units, of course, are simply moles. Now let me just see if you guys have any questions about that so far. All right. I'm getting a question here. Sir, what is the Google Classroom COD? If I don't know, are you actually in my class at CHS? If you are, you should know what Google Classrooms are. If not, if you're just one of my subscribers or something chiming in here, awesome. Google Classroom is used for all of our assignments and all of our grading system now that we've gone online. It's just simply something that Google provides, and it's got all of our stuff there. But it's just for our school. Okay, so wow, he's that famous. Well, I wouldn't put it that way, but you know, I do have over 20,000 subscribers. Anyway, now let's see. One more way to do this. So this is kind of the normal way, but there's another way that I want to look at this problem, and I want to think about this problem in terms of a conversion problem. Okay? So in terms of a conversion problem. So what do I mean by that? So we've done conversions before, and let me just pop this right in here. All right, we've done conversions before and used conversion factors to go from one units to another units. But we can think of this molarity, right, is 2.18 moles per liter. We can think of that as a conversion factor. Right? Just like you can think of density as a conversion factor between, let's say, grams and liters or grams and milliliters or something like that, you can also think of molarity or any kind of concentration as a conversion factor. Okay? So what is it? It's a conversion factor between moles and liters. Right? So when you have this solution, you have 2.18 moles in 1 liter of that solution. So if you have 1 liter of that solution, that's going to have 2.18 moles of whatever your substance is. So we can think of molarity in general as a conversion factor. And why is that important? Because it's going to make this stoichiometry a little bit easier. And so when we go back and look at the problem here, we have an initial amount. So what you say, how much of this calcium chloride do we have? Oh, we have 20 milliliters. That is the initial amount that you have. So you can say we have 20 milliliters, or you have 0.02 liters. That's the initial amount you have. And we have a conversion factor. The conversion factor between milliliters or between liters and moles is what? It's this concentration in molarity. So what we're going to do is take our initial amount and multiply by the conversion factor. And so that conversion factor is going to be, if we're starting off with moles, we're going to put if we're starting off with liters, we're going to put the 1 liter on the bottom, and we are going to solve for moles. So we're going to put 2.18 moles on top. All right. Now the math is exactly the same as before, right? It's just simply 2.18 times 0.02, and the answer is going to be, of course, the same. But the method's a little bit different. In this method, we use an equation, and in this method, we made the molarity into a conversion factor. Both ways are perfectly fine, but this way makes it a little bit easier for stoichiometry. It's going to make things a little bit nicer and neater when we solve these for stoichiometry problems. Okay? So, like I said, both ways are perfectly acceptable. Obviously, the math is exactly the same, but I want you guys to start thinking about molarity also as a conversion factor between moles and liters. So, any questions so far? Oh, look at that. Gilbert's online too. This is like my old AP chemistry class is joining us too. That's really crazy. Gilbert and Bourne, I don't know if anybody else is there. But anyway, let's hop on to the next question if you guys don't have any other questions about numbers 1 and 2, and we can go ahead and jump into that. Okay? So let's put these aside and come up to question number 3. Again, all of these problems can be found on Google Classroom. Hopefully you guys have visited Google Classroom and have checked that out already. Okay? So number 3, if we dissolve 10 grams, and let's switch this up. Let's do red. So 10 grams. Now this 10 grams, that's going to be a mass, right? And so that's not going to fit into our molarity equation per se. So 10 grams of aluminum chloride in water to make a solution with a final volume. And so this, once again, is our volume. We want that to be in liters. So our volume is going to be 0.33 liters. What is the molarity of the solution? So solving for molarity. And what do? We don't, molarity is N over V. We know V, but we don't know N. So we need to somehow calculate the moles, but we know how to do that, right? Because we have the mass, and we can always go between mass and moles. How do you do that? What is the conversion factor between mass and moles? Anybody know? Anybody in the chats? What is the conversion factor between grams and moles? What do I need to do? Let's see. Hopefully. Mn. Molar mass, right? We do need the molar mass, but not the molar mass of H2O, right? So molar mass is the conversion factor between grams and moles. But in this case, we need the molar mass of the solute, the stuff that we're dissolving. Remember, solute means the stuff that you're dissolving. We don't really, in this case, ever need to calculate the molar mass of water. Okay? So our solute is aluminum chloride, and aluminum chloride, once again, because aluminum has a 3+ charge. Well, how do I know that? I think you guys are really good at this, but just real quick review. Remember, +1, +2, +3 for aluminum, and it'd be -3, -2, -1 here. So aluminum is +3, and aluminum chloride you see here -1, right? So because aluminum is +3, chloride is -1, it should be AlCl3, okay? So that is, yeah, we'll talk about Dave later, okay? So that is aluminum chloride. We want to go ahead and calculate the molar mass of that. And the way we're going to do that is straight from the periodic table. All right, just make sure you guys can see this. And so aluminum is right here, and we can find the molar mass of aluminum underneath it. I don't know if you guys can see it because it's a little bit small there, and chloride is going to be right over here, right next to it. Okay, so what I'm going to do is I'm going to take the masses of those things. So aluminum is 26.982, and I'm going to add to that three chlorines, which is 35.453 to get the molar mass of aluminum chloride. Let's go ahead and type that in to our calculator. So 26.982 plus 3 times 453, and that's going to get us 133.341, which is the molar mass. 133, you probably don't need that many significant figures. And our units for molar mass are grams per mole. What does that mean? That means that 1 mole of aluminum chloride has a mass of 133.341 grams. Okay? So, done with this periodic table for now. Now that we have this molar mass for aluminum chloride, we can go ahead and solve for the moles. So, your N, your moles, right? We're going to start off with our 10 grams of aluminum chloride, use the molar mass. And guys, what's going to be on the top, what's going to be on the bottom, right? If I'm starting with grams, on the bottom is going to be what? 133.341 grams. And on the top is going to be 1 mole. Okay? So do your math. It's going to be 10. And if you have this in your calculator, you can simply do divided by your previous answer, which is the molar mass. Okay? And that's going to get you the number of moles. And that's a pretty nice number. That's 0.0750, just rounding up to 3 sig figs here, and that's moles of aluminum chloride. All right, so we're almost on the problem now. What's remaining is to plug it into that equation, m equals n over v. So molarity is the number of moles over the volume, which is 0.0750 moles over, we had a volume of 0.33 liters. So once again, we can just leave this number in the calculator, all right? It's key. You don't want to retype it, and also it'll save you from making any rounding errors, right? We're going to take this exact number and just hit divided by 0.33, okay? That's the way you guys should be putting this in your calculators. One, it avoids extra typing, saves you time. And number two, it avoids rounding error. You've got the exact number in your calculator, okay? So just hit divided by 0.33, enter, and that is your final answer for this one. It's going to be 0.227. And what are the units? Moles per liter. Okay? So that's going to be your final answer for number 3. Any questions on that? All right. Nice job, Henry. Henry got it. Looks like he got it before I did. Okay. Anybody else? Any questions? Any questions before we go on? Looks like we're going, everything's going pretty well. Let's do one more sample problem, and then I'll open it up to general questions. You guys can ask me whatever you guys want before the class is over, okay? So last question, we're now going to take this idea of molarity, and we're going to apply it to stoichiometry, all right? So this is what chemistry is really all about. Chemistry, I don't know what other people will tell you, but chemistry is all about chemical reactions. And so that's kind of the main point of everything we're learning is chemical reactions, so we can control matter, we can turn matter into something else, we can use the energy from that process or make other things. Anyway, a large piece of aluminum is placed in a 150 milliliter solution of 0.25 molar copper 2 chloride, and they react to form aluminum chloride and copper metal. Write out the balanced reaction. All right, let's do that. Balanced reaction. So we have, starting off, we have aluminum, and it's a solid, and we're going to react that. It's going to be copper 2 chloride. We know this 2 refers to the charge of the copper, right? The copper is a 2 plus charge, chloride is 1 minus, so that's going to be CuCl2, and it says it's a solution, so that of course is going to be AQ. And we're going to form, it tells us, you could maybe predict it, but it already tells us that's going to form aluminum chloride, AlCl3, that is soluble, and copper metal, which is a metal, as a metal, copper is going to be a solid. Okay? So it says we want to predict that, and of course we're going to balance it. Reactions always need to be balanced to make sure that we're correctly representing the reaction. So the first thing that we notice, we have 2 chlorines here and 3 chlorines there. So anytime you have a 2 and a 3, we're going to balance that by a 3 here and a 2 there. That's going to balance the chlorines to have 6 on both sides. But now you have 3 coppers, so we want to put 3 here. And we have 2 aluminums, so we want to put a 2 there. And everything's nice and balanced. Okay. Now, that's our reaction. What kind of reaction is that? Does anybody know what kind of reaction that is? Anybody? What kind of reaction is that? Now, I know there's a little bit of time lag, but Let's see what you guys come up with. Single replacement, absolutely right. That's a single replacement reaction. Or you can call it a single displacement reaction, something like that. That's fine. And let's get to the final question. What is the maximum amount of copper metal that, oh man, look at this typo, that reaction could, no, that's good. What's the maximum amount of copper metal that reaction could produce? Okay, so we want to know how much copper metal. Now, it doesn't honestly say whether it wants it in moles or grams, but we can go ahead and solve for either one or both. I would probably be solving for grams in this case. But let's set this up like any kind of stoichiometry problem. But we're going to do it a little bit differently because this now involves a solution, right? We have 150 milliliters of this solution. So we could split this up into individual steps, but I like to keep it all nice and neat in one big kind of conversion type problem. So I'm going to first write down this 150 milliliters. That's the amount of stuff we start with, right? That's the amount of stuff that we know. We have 150 milliliters, but that's we need to make sure that's in liters. So it's going to be 0.15 liters of what? Of this copper 2 chloride, okay? And we want to convert that into copper. We want to figure out how much copper that you can make from that, okay? And so the first thing that you want to do is you want to convert that into moles, okay? Because you can't convert from one chemical to another chemical in any other units. It's always moles. Well, why is that? Because the reaction itself tells you that 2 moles of aluminum react with 3 moles of copper 2 chloride to make 2 moles of aluminum chloride and 3 moles of copper, okay? So we need to convert that to moles, and like we said before, we could use the equation m equals n over v or n equals mv, or we could just simply use the molarity as a conversion factor, which is going to make this a lot nicer and neater. So we're going to make this at the top your 0.25 moles over 1 liter. Where did I get that? I got that right over here, okay? We have a molarity, this 0.250 m, that's moles per liter, and that's our molarity. Our molarity is the way that we're going to convert from liters to moles, okay? So that's going to be our first step. Everything else is going to be exactly the same that we've done already in stoichiometry. So what I'm going to do next is I want to convert from copper 2 chloride to copper, because it says what's the maximum amount of copper metal, all right? So we just look in the balance reaction. That middle step is always going to be looking at the balance reaction. And if I start with copper 2 chloride, I need to put copper 2 chloride, or 3CuCl2 on the bottom. The 3 comes from that 3 right there. And I'm solving for copper. So I look at the balance reaction and look at that. I've got 3 copper right there. So 3 copper. So fairly straightforward. Multiplying by 3 over 3 is really essentially multiplying by 1 or doing nothing. But you don't always have such nice, neat numbers there in these stoichiometry problems. Last step, now we could stop there and simply get moles of copper, but let's just go ahead and solve for grams of copper. And in order to do that, we need the molar mass of copper itself. And to get the molar mass of copper, we look back on the periodic table and look at, okay, copper right there, that's 63.546. All right, and we're going to put that on the top, 63.546 grams is 1 mole, okay? And so we see that, what are we doing in each of these steps? Before we even get the answer, let's see what we're doing in each of these steps. Here, we're going from liters to moles in this step. Here, we're going from one chemical, copper 2 chloride, and we're converting that into copper. In this last step, we're going to be going from moles into grams of our final stuff. Okay? So let's just do the math. And this is one that we definitely want to use our calculator for. Okay? Clear that out. This is going to be, it's just starting over here. It's going to be 0.15. I multiply by numbers in the top, divide by numbers in the bottom. So it's times 0.25 divide by 1, you don't need to put that in. Times 3 over 3, you literally don't need to put that in either because 3 over 3 is just 1. And then simply, last one is going to be times 63.546 divided by 1, which again, you don't need to put in. So that's all the math, 0.15 times 0.25 times 63.546, enter, and this is going to be our final answer in grams. And so let me go ahead and write that down. It's going to be 2.38. We do have 3 significant figures, right? 2.38 grams of copper. Look at that. All right. So somebody said 238 grams of copper. You must be off somewhere, probably in terms of maybe, I'm not sure. Maybe you used milliliters instead of liters or something like that. But the correct answer is 2.38 grams of copper as our final answer. Now, let's just suppose you wanted moles instead of grams. If you wanted moles instead of grams, you would literally just stop right here, okay? And so we can do that in our calculator real quick if we want moles also. How do I do that? I'm just going to hit second, enter, and all this comes up, and I'm going to delete the last part of it. Okay? Delete the last part of it. So 0.15 times 0.25 times 3 over 3 is going to get me the moles of copper. So if I wanted it, the problem doesn't specifically ask, but if I wanted it, that's going to be 0.0375 moles of copper. Okay? So that's pretty much all I wanted to go over today. And we are almost out of time, but at the very last part here, does anybody have any questions? Again, it looks like we're getting some numbers that are off by a little bit. Hi, Born. But make sure you pay attention to those decimal points. Make sure probably the biggest place where decimal points can get wrong are in here. 150 milliliters is 0.15 liters. And yeah. Any questions, guys? Any questions? That's Gilbert. Okay, cool. So class, is my class here? It looks like half the people here are from my AP chemistry class, just signing in for fun. But honors chemistry guys, what are you guys thinking? Do we need to know the molarity of water? Molarity of water wouldn't be really a thing that you're going to need to worry about. You could, let's say, solve for the molarity, and that would be an interesting problem, to solve for the molarity of this aluminum chloride, right? You could solve for that in this problem if we wanted to. And that would be another approach. Just the problem just asks what's the maximum amount of copper metal that the reaction could produce, okay? So if you want, you could also solve for aluminum chloride, the molarity of the aluminum chloride. How would you do that? The first part would be basically the same. This would be the same, and then it would start to be different right here. Okay, if you're interested, does anybody want me to show you how you solve for the aluminum chloride molarity? Anybody? Hi, Luke. Hi, Eliana. Hi, everybody. Anybody want me to show you how to solve for the molarity of aluminum chloride? Yes. All right. Happy birthday. Happy birthday. Happy birthday. All right. So let's go ahead and do that. If we were solving for the molarity of aluminum chloride, you would start off the same exact way. It would be 0.15 liters of our copper to chloride. We're going to make it 0.25 moles over 1 liter. That's going to get you into moles of copper to chloride. And now it's going to be different because we're solving for aluminum chloride. You're going to put your 2 AlCl3 on the top. And once again, on the bottom is going to be whatever you're starting with, our copper 2 chloride, 3 CuCl2 on the bottom. Now that's going to get you moles, okay? And we can that's probably the simplest way to do it, is just to calculate the moles. And at the very end, we're going to divide by the volume. We're expecting the volume to stay the same because the amount of water is going to stay the same, and the volume will be approximately the same although you might have a slight change in volume. Okay, so let's just go ahead and do that. Calculate the moles of aluminum chloride. So that's going to be 0.15 times 0.25 times 2 divided by 3 to get 0.025 moles of aluminum chloride. Okay? And if we want to get the molarity of that, you would simply plug it back into the equation, m equals n over v, and that's going to be 0.025 moles over the volume. Like I said, the volume hasn't changed at all, so it's going to be 0.15 liters. So last of all, we take that, divide that answer by 0.15, and that's going to get us a molarity of 0.16, rounded off to 3 sig figs, 7 moles per liter of aluminum chloride. Okay? But again, that's not what the question asks. That's just an extra additional application which you guys could do. But it's a great question. Great question. So we are pretty much out of time here. I'm going to go ahead and end it. Would you guys have any last minute questions at all? Okay, so I'm going to sign out. It's great hearing from you guys. And anybody else is still sleeping in, feel free, whatever, to check this out. It's going to be on YouTube. And see you. You're welcome. Alex, your Chinese is just awesome. I just want to say that. So good job with the Chinese there, Alex. All right. So see ya.